We are in section 4.2, logarithmic functions. This section is also an algebra review, so make sure that you reach out and ask for help if you're struggling with this section, either from myself or from the TMARC or from the ASAC tutoring centers. And so the first thing that we have is a logarithmic function is if a is greater than 0 and not equal to 1, then the logarithmic function of base a is defined by, and we have f of x equals log base a of x. Right below that we have some logarithmic rules that are good to know. First one is log of any base of 1 is equal to 0. The next thing is log base b of b. As long as that base and that value you're taking the log of are the same, then it would be equal to 1. 3 says log base b of b to the x power is just equal to x. And then 4 says log base b of x is equal to log base b of y if and only if x is equal to y. Number 5 says log base b of u times v is equal to log base b of u plus log base b of v. 6 says log base b of u divided by v is going to be log base b of u minus log base b of v. And then 7, the last one that we have here, is log base b of u to the n is equal to n times log base b of u. Next to the logarithmic rules that are listed is the graph of the log function. Again, this will depend on the base of the log, but it generally will have that same shape. The example right below says use the logarithmic rules to expand and simplify the following expression. And so we have log base 7 of 49x to the 5th over 5y to the 7th. So expanding this means we want to write it longer, so expanding it out. And so for this, I notice that we have a division here, 49x to the 5th divided by 5y to the 7th, and I'm able to use rule 6 and rewrite this as log base 7 of 49x to the 5th minus log base 7 of 5y to the 7th power. And then again, I can use rule 5 that's listed up above because we are multiplying in here. And so we can rewrite this as log base 7 of 49 plus log base 7 of x to the 5th minus, and I'll put parentheses since this is subtracting that whole entire log term. And so we have log base 7 of 5 plus log base 7 of 7y. And then from here, I'm able to simplify this a little bit more. I do note that we have log base 7 of 49, which is the same as 7 squared. And then the second term, I am able to use the last property that we have listed, 7, and pull that 5 out in front of the log. So 5 log base 7 of x. From here, I'm able to distribute that negative. And then I also note that that last term that we have is log base 7 of 7 to the y, which by looking at our rule 3, we can just rewrite that as a y. I'm also going to distribute the negative. So we have minus log base 7 of 5 minus, and again, this would just simplify to y based upon rule 3. From here, I still note that that first expression that we have here is log base 7 of 7 squared, which is just equal to 2. And so this would be equal to 2 plus 5 log base 7 of x minus log base 7 of 5 minus y. And that would be my final answer. Right below this, we have what's called the change of base formula. This says if x is any positive number, and if a and b are positive real numbers, then log base a of x is equal to log base b of x divided by log base b of a. The next two ways that this is written are useful in using the calculator in order to find our answers. And so for this, you'll notice we have ln of x over ln of a, and log of x over log of a. And on your calculator, you'll notice that you have an ln button, which stands for our natural log, and then we have an log button, which stands for our log base 10 or our common log. Right below this, we have a relationship between logarithmic functions and exponential functions, and these are inverses of each other. You can see on the graph over here, the bottom graph is going to be y equals log base b of x, and this top function is going to be y equals b to the x. And there's a special relationship here. They are inverses of each other, which if you remember from algebra is where you would switch your x's and y's and rewrite this. And so a little different here, since we do have a log and have an operation, it's a little different than adding or subtracting. Likewise, an exponential function. But this is key here to remember. So y to the bx is the same thing as x equals log base b of y. So these two forms, one's an exponential, one's in logarithmic, are equivalent to one another. For most students, we're not as comfortable with logarithmic form. So it's nice to be able to write things in exponential form. And so an easy way that I remember this is if I have log base b of y is equal to x, I just say that I take my base, raise it to the x power, and set it equal to y. So again, that base that I circled, raised to the x, is equal to y. And you'll notice that that matches up here to that exponential form. Rewriting something from logarithmic form to exponential form is usually easier for me to think about or to solve, and so it's a good thing to remember for the class. So this inverse relationship also means that e to the ln of x is equal to x, and ln of e to the x is equal to x for all x. The natural base e is commonly used base, however, this holds true for all bases. So we have an example on the next page that says solve each of the following equations for x. So it says log base 4 of x is equal to 1/2. And again, since this is in logarithmic form, it's easier for me to solve something if it's in exponential form. So I'm going to go ahead and rewrite that, just like what we just said at the previous page. So we're going to have 4 to the 1/2 is equal to x. So 4 to the 1/2 is equal to x. From here, I know that 1/2 is the square root. So this is the same thing as the square root of 4 is equal to x, or that x is equal to 2. B says log base x of 27 is equal to 3. So I'm going to go ahead and do the same exact thing and rewrite this in exponential form, which is going to be x to the third is equal to 27. So again, x to the third is equal to 27. And so we have some different ways that you can solve this, definitely taking a cube root on both sides, or you might just notice that x to the third equals, and 27 is the same as 3 to the third. And since these are both raised to the same power, we know that x must be equal to 3. Right below this, we have properties of logarithmic functions. The logarithmic function f of x equals log base b of x with b greater than 0 and not equal to 1 has the following properties. So the first one says that it is defined and continuous for all x greater than 0, and you can see that when you look at that graph of log on the previous page. 2, the y-axis is a vertical asymptote. 3, the x-intercept is 1, 0, and there is no y-intercept. 4, if b is greater than 1, then the limit as x approaches 0 from the right of the log function would be equal to negative infinity. And the limit as x approaches infinity of our log function would be equal to positive infinity. If b is in between 0 and 1, then the limit as x approaches 0 from the right of our log function is infinity, and the limit as x approaches infinity of our log function is equal to negative infinity. Again, taking a sec to look back at that graph that we had on the previous page. 5 says, for all x greater than 0, the function is increasing or the graph is rising if b is greater than 1, and decreasing or the graph is falling if b is between 0 and 1. Down below that, we have what's called doubling time. And so we know a quantity, q of t equals q naught e to the kt, where k is greater than 0, doubles when time is t equal to d, where d is equal to ln of 2 divided by k. So, good little formula to make sure you know. So we have some examples right below. The first one says, how long will it take $5,000 to grow to $7,000 in an investment earning interest at an annual rate of 6% if it's compounded. Part A says quarterly and B says continuously. So quarterly, I'm going to go ahead and write down the formula that we had from our previous section. So we have A equals P times 1 plus R over N raised to the NT. And we are given a bunch of information here. It does ask for how long, and that means we don't know T, but we do know we have $5,000, which is our principal, what we're starting with, and it grows to $7,000, which is our amount. And it also says we have an annual interest rate of 6%, which is 0.06. And we're trying to find T. It does say quarterly on this problem, so I know that N is equal to 4. So I'm going to go ahead and substitute in everything that we have. So we have 7,000 equals 5,000 times 1 plus R, which is 0.06, over N, which is 4, raised to the 4 times T, which we don't know. So from here, I can kind of solve this and simplify this before I have to actually worry about that unknown variable. So to simplify this, I'm going to divide both sides by 5,000. So we get 7 over 5 equals, and I can simplify what we have in that parentheses, which is 1 plus 0.06 divided by 4, or 1.015. And this is raised to the 4t. So now in order to solve this, I have my variable as an exponent. And to solve something where you don't know the exponent, we need to use the inverse of that exponential function, which would be a log function. And so the inverse of an exponential function is a log function. I'm going to go ahead and use ln, our natural log, but it doesn't matter which one you use. So I'm going to take ln on both sides of my equation. So from here, I have ln of 7/5 equals the 4 over t, using our properties, can move in front of that log, times ln of 1.015. To solve for t, I'm going to divide both sides by 4 ln of 1.015. So we get t is equal to ln of 7/5 all over 4 times ln of 1.015. I'm going to work this out and just round 2 decimal places, and we get 5.65. And since we're dealing with time here, remember time with these formulas was expressed as years. So it's going to take about 5.65, a little over 5.5 years for this investment, which is $5,000, to grow to $7,000. Part B now says that it's compounded continuously. So remember, we have a different formula. It's A equals P e to the RT. So I'm going to substitute everything in. We know A is 7,000, P is 5,000, e to the R, which is 0.06 t. And so again, isolating that part of the problem that has the unknown variable, I'm going to divide by 5,000. So we get 7/5 equals e to 0.06 t. And then again, this is an exponential function. Since I do not know that exponent, I need to use the inverse of an exponential function, which would be a log function. I'm going to use ln again. So putting ln on both sides of my equation, we have ln of 7/5 equals, and now since ln is equal to log base e, we can see that this base and the expression that we're taking the log of have the same e. This would just simplify to 0.06 t, which is using those properties that we have on the previous page. And so to solve this for t, I'm going to take ln of 7/5 and divide by 0.06 to get my t value. So substituting this in on my calculator and rounding 2 decimal places, we get 5.61 years. The next example says if Hubert invests $1,000 at 8% annual interest and it's compounded continuously, how long does it take for his investment to double? So that formula for doubling time is listed right up above these examples. And you can see that for this, we need to find our time. And so there's two different methods to do this. One is using that formula and another one is not using the formula. So I'm going to go ahead and work this out, both methods. So split the paper. And so the first one is if you have $1,000 and you want it to double, that means that when you double it, you would have $2,000. And so since this is compounding continuously, I know that my final amount would be 2,000. My starting amount was 1,000. E to the R, and our rate for this problem is 0.08, which we're given, and then T, which is what we don't know. So dividing both by 1,000, we get 2 equals E to the 0.08T. Again, just like what we did before, taking the natural log on both sides to isolate that variable. We're going to have ln of 2 equals, and the right hand side is just going to be 0.08t, and then divide both sides by 0.08. We get t is equal to ln of 2 over 0.08. And so if you look at this, this will actually match what we had up here. And so our formula that we had up above was ln of 2 over k. If you notice, k is that rate that we have. And so we have ln of 2 over 0.08. So that's matching what we had given to us. And so for this, when we work this out, for either one, you're going to get your time is equal to 8.66, and again, our unit is years.